Hello, good afternoon to everybody. I'd like to start by recalling the main topics. I will begin with a light introduction to diffusion, which is like a common thread of what I have been doing for several decades. And then I will pass to fractional diffusion, which is a topic for the last, let's say, 10 years. And number three is what I will really do today, which is trying to develop a theory for the p-Laplacian operator, which means fractional because of the S and nonlinear of p-Laplacian type because of the P. And then the last part is explaining to you the work that I did in the last months about the fast version of this p-Laplacian fractional operator. So the beginning should be relatively easy, and probably all of you know that, but just in case, because I see that there are huge amounts of people. Okay, as usual. And the idea is that for a person in the natural sciences, diffusion is well established as a concept, and it describes how a continuous medium, for instance, a population, spreads to occupy available space. And there are many models which realize that idea in practice from all kinds of applications, like fluids, chemicals, bacteria, animal populations, in particular the Newtonian fluids that go into Navier-Stokes, and there is diffusion in the stock market, so it is very well documented. And the point is that this natural phenomenon has rich mathematics. So the question for us is, what is the diffusion for a mathematician, and how do you analyze the diffusion in mathematical terms in an efficient way? And this question took some time to develop. It has been developed very strongly in the last century, and there are two standard answers, which are in principle very different, but then we have been trying to mix them. One of them is the idea that diffusion is related to random walk and to its continuous limit, which is the Brownian motion. And this is a correct answer. It has been verified in many applications, and the approach leads to Brownian motion and then more generally into stochastic processes. And there is a famous equation, which is called Ito equation, developed by Kiyoshi Ito in the period 42 to 50. So it was the middle of the last century. And the equation looks like typical ordinary differential equation, but it has a term hidden here, this dw, which is the increment of the white noise. And this is complicated to tackle unless you develop a very sophisticated theory. So this has been done. It makes for lots of study, but it is for us interesting to go to the second approach. Second approach is that you can start from the heat equation. And this was proposed before by Fourier. And in the 1930s, before this development of Brownian motion in full force, Andrei Nikolaevich Kolmogorov in Moscow developed this idea that there is a connection between the PDEs and the stochastic processes. And so there is a translation from the equation number one to equation number two. And this is very rich in consequences. So understanding how this double wave works is the source of much of the effort of people who are working in these fields today. And we will follow, since I am an analyst, the way of analysis, which had been inaugurated, everybody knows that, in analysis by Fourier around the beginning of the 19th century. And it was proposed by as a model for heat propagation. At the time, nobody knew that heat propagation had nothing to do with any kind of Brownian motion or whatever. So it's an instance of practical modeling. So some of the problems we face today, and we want to give answers here, is that how much of this can be explained by linear models and how much is essentially nonlinear. And this is important for us because I belong to the groups of nonlinear analysis, like many of you. So we are interested in trying to find a niche for our work that is justified in physical terms. And then second point is that the stationary states of diffusion belong to an important world in applied analysis, which is elliptic equations. And then elliptic equations, both linear and nonlinear, are like a core, the center of PDEs, and they have many relatives. They come not only from diffusion, also from fluid mechanics, from waves, from quantum mechanics. So it's a very rich theory. In fact, it is like a center of what we do. So in some sense, there is an arrow that goes from elliptic to parabolic, and the arrow from parabolic to elliptic is like a different arrow, dependence. And then what I will say is that among the different operators that we can use, there is one that is really the king of what we do, which is the Laplacian operator. And Laplacian is not only very strong in analysis and PDEs, it's also very strong in numerics and very strong in geometry. So it has a pivotal role in all of these applications of pure mathematics to the natural world. And one of the things that has been developed recently is a relative of the main Laplacian, the real king, one of the family members, is the family of non-local, long-range operators of Laplacian type. And this is, for instance, the fractional Laplacian that I will use today. So the question is, are we able to use all of this machinery to treat complex systems, and for instance, to use treat systems and understand and isolate the influence of different terms that come into the equations? Well, in order to do that, you have in our communities people who are very good at modeling, other people are very good at analysis, other people are very good at stochastics, and other people do very well asymptotics, other people do numerics, and if you go on, there are people who are very good at geometrical PDEs and so on. So the question is, what do I do for you today? I will do 1, 2, 3, 4 is the important thing for me. I will have to do a bit of modeling, a bit of analysis, no stochastics, no numerics. Well, yeah, numerics was not done for me, but the asymptotics is what I want to contribute. It's a beautiful thing that says that the limits of the evolution of complicated data for these diffusion equations are simple, beautiful diffusive profiles that have lots of symmetries and lots of good properties of functional equations. And I will not talk about what I did before, but it is, I want to make some propaganda for the fact that part of these things that I have been doing recently is already documented now. And I wrote a summary several years ago in Cetraro, in a beautiful summer course in the south of Italy. It has been published by Springer Lecture Notes. And these are the people who were my co-teachers in the course, and these are the editors. So it's like a mention of friends. So let me go to fractional diffusion without more loss of time. Okay, the idea of replacing Laplacians by fractional Laplacians is motivated by the need to represent something called anomalous diffusion. And this anomalous diffusion had been observed in different phenomena. It is not as usual as common diffusion. So in any case, the main role is for Brownian motion and heat equation. But everybody knows that different versions of even the heat equation were going around under the name of semilinear or quasi-linear equations due to the needs of really practical applications. So it is not surprised that if you find something called anomalous diffusion, you want to model it and you want to know if it is related to the heat equation or not. Well, in probabilistic terms, the people who found that phenomenon understood that they had to replace random walks by, and their limit of random motion by something called long distance interactions. And the idea is that the particles will not bump into each other like in Brownian motion, but they will have an influence long away, very, very far away from the place they are. And this is very important nowadays because of the age of information theory. You may have significant interactions without moving from your chair with people who are sitting peacefully in Bangalore or in Beijing. So you have to take into account this idea, and this was taken into account. Now, the second thing I want to say is that for the people in analysis, there is good news. The representative of these long-range fractional operators is something that in analysis has a symbol, and it has a name. And the symbol is minus Laplacian power s, whatever it means. It's very important that it has a symbol. And then it has a name, fractional Laplacian, because it has power s, and s goes between 0 and 1. If you go to the parabolic version, which is the equivalent of the heat equation, then the equation will be ut plus minus Laplacian to the s. People in the trade know that you cannot take powers of the Laplacian because Laplacian is not a positive operator. So the calculus, the operational calculus, which is based on negative operators, works very well for minus Laplacian. So this doesn't need any further explanation, but it leads to a certain awkward notation. This parenthesis minus delta parenthesis s is a bit awkward, but it's very quite natural for persons who know what is the meaning of the minus Laplacian. Okay, so the beginning of this work in understanding long-range interactions belongs to the people in stochastic processes, and the fractional Laplacian was known also in harmonic analysis, but the connection between the two things was not clearly established, or at least not used a lot. Only recently the predominance of the probabilistic methods to deal with anomalous diffusion gave way to the analysis using PDEs because of the need of treating nonlinear operators. And nonlinear operators are better treated in PDEs because we have these wonderful ideas of integrating by parts that are not so amenable to stochastic methods. So I knew from this idea of using PDEs to work on the different kind of diffusion from my master Caffarelli when I was in Texas visiting him. And I read the paper who came from the thesis of his student Luis Silvestre, which is a beautiful paper, one of the standard papers of this trade. Maybe the best known of the papers in this development of the theory of fractional Laplacian for analytic purposes. So everybody probably knows here more or less what is going on. I will only recap that if you're an analyst, you want to begin by sound foundations, and the best foundation for an analytic approach to the fractional Laplacian is to take Fourier transform and look at the symbol. And the symbol is xi to the 2s. So you see there why we call it a fractional. It's fractional in Fourier space because it takes a fractional of the symbol. Now, if you want to go back this product to anti-Fourier, this product, you get a certain convolution, which should give you something like this integral without the difference upstairs, because this is not a convolution. This integral I am putting here has a uy over x minus y to the n plus 2s, and then you see that uy comes from hat u, and x minus e to the power n plus 2s comes from the c to the 2s. But this integral is divergent, and you have to renormalize it. And this is where you put an extra ux in the numerator and try to understand if this new object is convergent. This was done many years ago by, in particular, Eli Stein and the Russian Naum Lankov, and it's very well known people in harmonic analysis, so I will not. But this is the standard definition of the fractional Laplacian for the people who want to do integrals of things. Next thing is that you have to recover what the people in probability know, and then you have to try to understand that the people in probability use the Markov rule to pass from the discretization at time t equals tn to t equals tn plus 1 at the site x equals xk and to the site x equals xj with a certain Markov rule with transition probabilities. You do it and you find that it in the limit, you get the same operator. This was done, first time I saw that, it's in a beautiful paper published in Spain by Enrico Valdinocci, our friend. Okay, then there is this extension method by Luis Caffarelli that we used so much. I mention it because I will not use it, so let me jump on this. And then there is something called the semigroup formula that allows you to define the stationary Laplacian, fractional Laplacian, in terms of a kind of Laplace integral of the heat flow. So you get the heat flow, which is an evolution semigroup. You make this integral and you find this gives you the stationary Laplacian to the power s. Okay. So let's start now with the real analysis of parabolic equations. The first equation you want to treat is the heat equation in fractional version, which is easier than expected. It's just putting this parenthesis to the s. And if you want to do that, it's not difficult to do it. You generate a semigroup, and it represents the Levy process. You can do the stochastic process, the analytical process, the numerical process in three things in parallel, and it worked very well. So there is no problem in developing a theory. And what happens is that more or less following the idea of the heat equation, you get a representation of the solution in terms of an evolution kernel that we call capital P sub t. And this capital P is the Green function. But the Green function of this operator, the fractional operator, is not an exponential. And in the case where s equals 1/2, which is the typical fractional case, the simplest of the fractional cases, they get an explicit formula in terms of the Poisson semigroup for another thing. But in case S is any fractional number, you only get approximation in the sense of limit with a kernel where you don't know exactly the formula. You only get an idea, an estimate of the approximation. And then what happens is that it takes some time to develop an existence and uniqueness theory under the condition of optimal data. This is something that we did not many years ago, 3 years, almost 4 years ago, with Matteo Bonforte and Yannick Sire, just to make, to write the paper clearly for the students. So this is something done. And after that, there were several models, and I want to study one of them. Let me see which are the typical models that you find. So you start with the heat equation, and then you go to the porous medium equation. Well, I go. It was my life. And then if you do porous medium and it works, so the power is here, is u to the m is not 1, then you can do in parallel the p-Laplacian. And you find that the theories are similar, but they are not the same. So there is a duality. You have to work a bit in parallel and work a bit in a different way. So while the heat equation is an example of an analytic semigroup, linear, both the porous medium and the p-Laplacian are beautiful examples of nonlinear semigroups with strong properties because of these invariants associated to the powers. So it gave lots of impetus to development of the nonlinear semigroup theory for PDEs. And if you want to be more precise about the applications, you can put p equals 1 and you get the total variation flow, or p equals infinity and you get the infinite Laplacian flow, which are curious things, but they work very well. And many people have been trying to work on them. Okay, if you now work on fractional level, you go from up down to the heat equation in the fractional case, which I have considered. And then what happens if you want to go from here and mix them? Well, you get the fractional porous medium. And this is something I was doing with my collaborators in Madrid for a number of years. And we were really very happy doing that because it was, I mean, it had beautiful properties, but they were not so easy. There is another model that I didn't write the formula correctly 1 hour ago when I wrote this picture. There is the Caffarelli model of fractional porous medium, which we call the model with fractional pressure. You have to put a minus Laplacian here to a certain power here. Okay, so now in what I will do today, I will try to do the same thing that is done for porous medium for another operator that has to be the p-Laplacian in fractional version. So the first question is, what is the natural version of the p-Laplacian in the fractional level? And this is what I will do next. Okay, is there any question now? Okay, so do you hear me well, or is there any problem?
Loud and clear.
Okay, so let's start with the real talk. There are several possible approaches to define a p-Laplacian operator p-Laplacian operator with fractional origin. And the simplest one, to my mind, is to begin the theory with the calculus of variations approach to what is the real standard p-Laplacian. And the idea is Laplacian for the standard people is the subdifferential of the P energy, and the P energy is the integral of the derivative of u to the power P. So in case you get P equals 2, the P energy is the Dirichlet integral, Dirichlet quadratic integral. So the difference now is knowing which is the fractional energy. And that's not so difficult. Once you begin thinking in that direction, you discover that there is a fractional energy that is well known, that is the Gagliardo seminorm. And this is the basis of the definition of the WSP spaces, fractional Sobolev spaces, also called Slovodetsky, Gagliardo. There are several names. So now you begin with your definition of your spaces. You define the seminorm, the PS version of the seminorm, which is just defined with this integral. And then you can define the complete norm by using the LP norm plus the seminorm. And then you are in business because you say, once I know that this works, and people knew that it works many years ago, like 40 years ago or more, then you define the subdifferential. And subdifferential is just an operator that you do Gato derivative here and you find this thing. Where this capital Phi, I don't want to write a complicated version for what I call usually the French Laplacian. The French power. The power where you define the, for instance, the cubic function like an odd function. All of the powers are odd functions. So you have to write it this way. And once you find this definition of the operator, you want to solve for elliptic or parabolic problems using this operator. This has been done in the last 10 years. And what I will do today is to present to you two papers written this year under the terrible pandemic time. One of them is already published. It is the evolution fractional p-Laplacian in Rn, and I want to find the fundamental solution in the asymptotic behavior. And this is like in many of my other papers, an homage to my master and friend Grigori Barenblatt, who died recently after promoting fundamental solutions for nonlinear evolutions all his life. And the second paper I want to tell you is something that was completed very recently, is the sublinear case of the same equation where instead of p larger than 2, you have p less than 2, and then you enter into the fast diffusion problematic. So in both cases, I want to study the evolution equation. Evolution equation is number 3, which is just the gradient flow. So you get I repeat, the Gagliardo seminorm, which is 1 over the power 1 over p of the Gagliardo energy. And then once you get this, you take the subdifferential, which is a maximal monotone operator in L2, which is beautiful. And then you make evolution. And it looks like the theory of maximal monotone operator should work. Okay, you put initial data and you choose for your space, the whole space or bounded domain. And I am choosing here the whole space. I will explain to you why. And then there are the two ranges that one in principle should think that should be very similar, but they are not similar because the details in the case of the fast diffusion really complicate all the time. So the questions I want to solve is the asymptotic convergence of a wide class of solutions and with determination of the exact rate of time decay and the exact description of the asymptotic space profile. In the heat equation, the time decay is t to the minus dimension over 2, and the space profile is Gaussian. And in the rest of the cases that have been examined in the theory, there is something that is the answer. The question is, can I do it here? Okay, so let me see what I will find. If I'm using the heat equation, sorry, there is a U missing here. In a bounded domain, then at the asymptotic level, there is separation of variables because there is Fourier analysis working here in the sense of Fourier series. And you take the first term of the Fourier series development because it has the lowest coefficient in the exponential decrease in time. And the constant is just the projection of the first eigenfunction on the initial data. But let me call it C of U naught. This is what happens in a bounded domain. Now, if you work in Rn, this is not true. You go to the Gaussian. And then this constant is a function of the initial data, but it's just the initial mass. So there are two different worlds. And I want to choose one. Well, in fact, number 1, which is the bounded domain, was studied like several years ago by a number of people, in particular José Manuel Mazón, Julio Rossi, and Julián Toledo wrote a nice paper on the fractional p-Laplacian evolution, and they did the basic theory with lots of detail, which is good. And there was another paper that we used at the time, which was a paper by Pust 1 year before. And in parallel, I was working on what I try to do all the time, which is asymptotic behavior. So I did it, and I found the separation of variables, which is not this one, but it works. And I found that phi is the solution of a certain nonlinear eigenvalue problem that you can isolate. And in fact, Lindgren and Lindquist were working on the elliptic nonlinear eigenvalue problem. So this is for p larger than 2, and this is for a bounded domain. And what I will do now is dealing with p larger than 2, but in a whole space. And then you start with a problem consisting of equation 3 with initial data 4. And you discover that this theory of maximal monotone operators works very well in L2, but in fact it works very well in all LQ spaces, because this operator is completely accretive in all LP spaces. And this is a beautiful property that was developed by Philippe Benilan and his friends. Okay, so you are in business because the theory from the point of view of generating a nonlinear semigroup cannot be easier. So you have to do the calculations, but at least you have a solution constructed as a continuous, strong solution that corresponds to the theory of generation of a nonlinear semigroup as developed by Brezis, for instance. Now you have to develop the properties if you want to do the asymptotic behavior. Otherwise, you don't get a convergence to nothing. So one of the things you have to prove is that solutions in L1 become bounded immediately, which is one of the typical features of these theories. The bounded regularization of L1 solutions. And this was proved in a preprint by Bonfort and Salor that has not appeared. And there was next to that a proof, a bit more of the proof of regularity, proving all the regularity when the solutions are bounded. And this was done by Lorenzo Vázquez, Lindgren, and Strömquist. Okay, then you need lots of small tricks that of the trade, like Alexandro principle to make symmetries and prove that the solutions have a certain geometry when T is large. And this asymptotic geometry based on Alexandrov's principle is called almost radiality. It is very good for asymptotic behavior. And then you discover that one of the typical features of the p-Laplacian is false in this case. Solutions that begin with non-negative data, even if they have compact support, we lose the compact support immediately. There are no free boundaries. It's a bad news for the people in free boundaries, but we cannot do anything. So you think, and now how do I pass to the limit if diffusion tries to spread the solution so it's difficult to see it? And then there is something called the renormalized flow that is based by many people in PDEs, in geometry, in waves, try to understand what is the object that up to scale will have a shape that you can see at size 1. So let me tell you the results. First result, this is the existence and uniqueness of the model of asymptotic behavior, what I call the Selfsimilar fundamental solution. There is for every mass, initial mass, a unique Selfsimilar solution of this special form, separated the time in the factor outside, and factor inside. The M's are simply because the mass scales very easily. I put it here, it will confuse you a bit, but it's just that it's handy for me to have the mass scaling perfectly on both sides. And then this capital F is what plays the role of the exponential in the heat equation. And this capital F is what we call the spatial profile. And the first thing that you know about self-similarity is that the exponents of this formula are relatively easy to calculate using dimensional analysis. But calculating the profile is not easy. So f is the continuous positive radially symmetric function, and we know that it goes to zero like a power because we expect those long-range interactions to produce not exponential decay but power decay. I was able to prove the correct power decay according to all a priori calculations. And then this is the first result, producing the asymptotic model. And now the second result is, before the second result, I asked my collaborator and former student, Felix Del Teso, to produce the pictures using the evolution scheme that underlies the equation. So instead of solving the equation of the profile, we solve the real evolution equation, renormalizing all the time according to the size that we knew what should happen. And this is for different values of the exponent p, and for s equals 1/2, the asymptotic profile. You see that it depends on the s. When s is, when p is very large, it begins to have kind of mesa that is not expected. I still don't know why there is a mesa in the p-Laplacian. There is a mesa in the porous medium, not in the p-Laplacian. Now, since Felix is a good numerist, he did the logarithmic scale computations to show clearly how these tails look like lines. And the lines have to be the power that I want them to be. In one dimension, the power of the exponential of the powers, the exponent has to be 1 plus sp. S was 1/2, so 1 plus p over 2. And it really agrees the predicted decay with the computed decay. So it's a wonderful thing because it converges relatively quickly in a table computer. And this is the same computations when instead of changing the p, I change the s. And again, the log computations show perfect tail agreement. And this is the asymptotic behavior theorem that really I wanted to prove. The idea is that if you take an initial datum and let it evolve according to the gradient flow of the Gagliardo norm, and then you take this ideal solution constructed by Selfsimilarity, the difference as t tends to infinity in L1 tends to 0. And in L infinity not only tends to 0, it tends to 0 even if you amplify by the factor t to the alpha, so that you make it unit height. It has been decreasing all the time because in evolution, but then you zoom it up with t to the alpha, still this difference goes to 0. And this is what you prove for the heat equation, so this is what has to be proved. And this is the end of the first paper. And the idea is that fundamental solutions are a basic ingredient in the theory of heat equation in linear parabolic equations. So what I wanted to do here was to do the development of this theory for the fractional p-Laplacian. For the porous medium was well known. For the p-Laplacian standard was also known. And the proofs, rigorous proofs, took a long time, but they already were more or less finished around 2000. And then Fast diffusion took a long time to develop, so I go to that. And then in the case of nonlinear fractional, the work is past 2010. I did for one of the models of porous medium with Caffarelli, the asymptotic behavior using entropies. And for the other model, I did the asymptotic behavior using dual equation. And in this case, both approaches don't work. So I had to do a completely different proof. And it took me 1 year until I found the idea. And the idea was to construct a sharp upper barrier. So I had some a priori estimates and I had some compactness. The problem is, why is it that the solutions do not go away in a way that I cannot control things that converge to something that is not zero and not infinity? And this is what provides the upper barrier that looks like more or less like a function I was trying to find, but only approximately. And you don't do exact solutions, you do super and sub-solutions, which replaces the difficult computation by approximate computation, which you can do. And then once you have this upper barrier, you use the whole machinery that is based on scaling transformations, the L1 infinity effect, conservation of mass, local compactness in sublevel spaces, strict positivity, and a certain Lyapunov functional for L1 differences in L1. And you produce the theorem. Okay, so the problem is in the end of the talk, what do you find in the sublinear case? Is it not true that p less than 2 should be similar to p larger than 2, only changing the numbers when you need to change them and making some modification of the lemmas? And the answer is no. The results are sometimes relatively similar, but in many cases very different. And the methods are also different. One of the things that appears immediately is that when p is less than 2, it begins to look funny. And there is an exponent, intermediate exponent, 2n over n plus s, where the whole idea of this Barenblatt approach breaks down. So I decided to push the theory until it breaks down to see what happens. And it took me 70 pages. I tried to cut it and cut it. There was no way. I cut from 100 pages to 70. And here is the theorem. First theorem looks very different, very similar. There is a similar solution. There are exponents of similarity. The profile is a certain continuous positive and radially symmetric function. Decrease is like, I will tell you later. Of course, it begins with the Dirac mass. And if you go beyond PC, the critical exponent, there is no such solution. The theory is yet to be done. PC is this critical exponent is exactly the exponent for which the denominator here goes to 0. So if you want to do dimensional analysis, to do self-similarity, it breaks down here. So the breakdown at PC is expected for the experts. And then you can do all the calculations for m equals 1 because we have beautiful scaling. Curiously, in the standard non-fractional case, this profile is explicit. It's the famous Barenblatt profile. So why is it that we cannot do it here by trying to do something relatively explicit? Okay, you cannot do it. It doesn't work. It is not explicit. But even if you want to do approximate calculations, you have to do computations of this thing, which is a power of a sum of 2 powers. And taking this fractional operator on this thing is not very easy. So this is what it takes a long time. it is no good trying to use this as a super and sub solution because the computations are too difficult. And then when I want to know what is the decay of the profile, I discovered there is another exponent where it breaks down. Let me call it P1. And it has a formula. So I jump on the formula and I discover now that I can tell you what is the first result in the fast diffusion where things are different. It says, if you go very far from p equals 2, then there is a behavior that looks like what was expected in fast diffusion. But if you are not very far from 2, the behavior is what is expected in fractional diffusion. And you don't see the nonlinear, no, you don't see much of the fractional nonlinear. So there are two profiles. And one of them is what I will call the fast diffusion exponent, and this I will call it, because it's the same as the previous proof for p larger than 2, the fractional exponent. So there is a breakup of the theory when things lose the fractional tail and begin to have the fast tail. And this is the graph. So this red line is n plus 2s. M is the fractional tail. And when you get here to P1, you begin to get the fractional tail. And the idea is that the tail will be the greater of the two things. So it diffuses at least like one of them. And since the two tails are not the same, it is the worst case. And when you get to PC, something breaks here in the coefficients, and you cannot continue doing these things because the solution disappears, because there is no capital F anymore. Okay, so this is asymptotic behavior. The asymptotic behavior is stupidly simple because it says that in any case, the Barenblatt solution in the fractional case will be true. But it is deceptive because you have to work so much to produce the solution. Well, the idea of producing these solutions, to give you an idea of the proofs, and I will try to finish, is that you cannot pass to the limit in the solutions like they are presented to you because they go to 0. So you have to renormalize them, and you say that you will begin to decrease like t to the minus n beta, and I separate this coefficient because this is a decrease factor. And the rest of the thing, v of y tau, will not be decreasing. And this is the renormalized solution that I want to study. And then y will be renormalized also in order to avoid it from spreading. And the time has to be logarithmic. Experts know these tricks. We have been doing these tricks for 20 years. And if you write the equation for the v, it has this funny way, it's autonomous equation with a Fokker-Planck confining term. And you have to find a solution for this thing by passing to the limit but compactness. Okay, and the idea is that you will prove that things will be bounded uniformly above and below, so they will try to converge to something that is stationary. And it is difficult to prove that there is a stationary object here. You do fixed point theory for this equation. And then you will eliminate at the end d tau of v. And what you find is the solution of an elliptic equation that looks like looks a bit like nonlinear eigenvalues, and in fact they are. Well, once you know that there is the solution that you will use as the stationary profile, here is the mother of all the problem. You have to find the solution of this. And you know that there is an evolution of approximate solutions of these that will be forced to converge to equilibrium. I want these approximate solutions not to escape, and I will do barriers for that. And on that equation, I will construct barriers that decay as predicted in the main theorem. So I have to find the solution before I prove the solution, and even before I construct the barriers. And again, we get, thanks to Felix, we did the computations, the profiles. They are not so rounded. And curiously enough, I will tell you last moment improvement. I did the whole theory for p less than 2 with a problem that I didn't have a theorem on regularity of solutions, on bounded solutions. And if you have regularity of bounded solutions in a C alpha class, you get beautiful compactness. And I needed this beautiful compactness uniformly in time for the renormalized flow. So I had to work and work and work a lot for p less than 2 to produce the theorems by using tricks and not using C alpha, because I didn't know C alpha. And after the paper was finished, I was looking around and around. Finally, Antonio Giannizzotto was good enough to answer one of my questions and tell me where to find a way of proving the parabolic C alpha result using the elliptic C alpha result that he had proved. So this is very beautiful. I thank very much Antonio. This was done in December, and the paper had already been submitted, so I had to try to publish in archive a new version that eliminates all of these frantic technicalities. Okay, and in the last part, I was trying to talk to you about very singular solutions. That is a typical thing of the parabolic theory. But I understand now that I don't have time. The first blue thing, number 21, is the famous very singular solution of the fast diffusion equation. And 22 is the parabolic, the elliptic equation with the singularity at the origin. This is something that people in elliptic fractional equations have been doing. Even in Spain, I remember Maria del Mar does lots of these singularities. Of course, Luis Cafarelli does also. I did work on that. It's a work that produced a theorem that I like. It says that this power profile produces a solution of this strange elliptic eigenvalue problem in the case 1 less than p less than pc, in the case p equals pc, in the case pc less than p1, and not in the rest of cases. And the solutions have very different singularities. And with that, I will try to, I have a list of open problems that I cannot read now because, well, there are problems that you can check. And I will thank you for your attention and answer some questions if needed. Thank you.